Okay, the lecture today is going to be about symmetric matrices. You remember what made this matrix to be symmetric? Essentially, we defined it. A matrix A is symmetric if when you transpose it, you get the matrix itself. In other words, the numbers that appear across the diagonal are the same. So on the diagonal, I could have anything I want, like 2, 3, 5, etc. Across the diagonals, the numbers should match. The number that is sitting at the location ij and ji must be same. So here, if I have 7, here I'll have to have 7. Here, if it is 9, this is 9. If it is 0, that has to be 0. Implicit in the discussion is that we are only talking about this in the context of real matrices, even though it's not directly mentioned and sometimes not relevant, but we only consider real matrices. The entries are real numbers as opposed to complex numbers, and we actually need to talk about complex numbers today. Okay, for symmetric matrices, we have lots of good news that these matrices have some nice properties. It makes handling them very easy and comfortable. Let's go back to see what the issue is and what's the main property of symmetric matrices we are going to use. We have been talking about the eigenvalue problem, that if you have a matrix A, there are some special vectors that when you multiply matrix with that vector, all that happens is that that vector gets to be magnified by some number. The way to find this was to set the determinant of lambda minus a equal to 0, get your characteristic polynomial and get its roots. But when you are dealing with polynomials, it's always possible for the roots to be complex numbers. It is possible for the roots that you're after, the roots are going to be lambda, to be complex numbers. Well, that's going to throw things off. We didn't practice this thing really enough to talk about it extensively, but we can see the possibility. If the lambda turns out to be complex, this lambda is going to be complex. Once lambda is complex, x is also going to be complex. You haven't dealt with vectors whose components are complex numbers. It's kind of, we don't have much visualization for that thing. And when you talk about that output vector being an extension of the input vector, the idea is not that simple anymore. Like when you're doubling a vector, well, it stays in the same direction it was, it just becomes twice as long. But if your vector is a complex number, and so is lambda, multiplying them throws things off balance quite a bit. The idea of extension is not as easy as before. So if lambda is a complex number, then the eigenvector will be a complex vector. And truly things become complex. Like visualizing them becomes totally impossible, because in the smallest case you want to consider, smaller case of a vector is a vector has to have two components. Each of them is a complex number. Already you have 4 numbers to deal with. That is, the simplest case to consider is a 4-dimensional case. And we cannot visualize in 4 dimensions. So things are, in a sense, truly complicated. Question is there any situation where we have guarantees that we are not dealing with this complication? Is there any case that we know ahead of time we are not dealing with anything complex anywhere? Lambdas are not complex, x's are not complex, everything is just in a comfortable, familiar surrounding. And the answer is a resounding yes. One very major case where we are guaranteed we are not going to see any of these things is the case of symmetric matrices. If matrix is symmetric, life is nice. So here we have the following theorem. Very big idea. If A is real symmetric matrix, then lots of properties are going to follow. Let me write them one by one and try to see how much of this we can explain today. Then all eigenvalues are real. All eigenvalues will be real. Now, let me go back up a little bit and just say that it's quite easy to end up with a situation that eigenvalues are complex numbers. Let me give you the easiest case. So, see if we can fit it in that little box there. Suppose I have a matrix A, not symmetric of course. Here, let's take the easiest one, 0, 1, minus 1, 0. Tell me what is determinant of lambda minus A. So lambda is going to be, lambda minus A itself, let's write that one first, and then you tell me what's the determinant of it. Lambda minus A, here I'll have lambda minus 0, 0, so I have lambda here minus A, so it's going to be minus 1 and 1. So what's the determinant of that thing? Lambda squared, what's that? Plus 1. Here is the root of all evil, if you wish. If you set this thing equal to 0, what's lambda? Well, lambda squared will be minus 1. Square root of minus 1, well, it's not a real number. And you end up very easily with square root of, that is the easiest, simplest case where eigenvalues turn out to be complex numbers. These are very important. We are not saying they are unimportant. In fact, when you want to describe rotation, you end up with this kind of situation. Rotation matrices, rotation can be represented by matrix. Those matrices have eigenvalues which are complex numbers. We kind of avoided them throughout the whole semester. So they are both important and common. Here we are saying, if you are beginning, at the very beginning, you know that you are dealing with a real symmetric matrix, that kind of a situation cannot happen no matter what numbers you put here. Imagine you have a lot of leeway. You can do all sorts of things here. So long as these numbers match, eigenvalues are going to be real. Next, we came across quite a few situations that where we were trying to find the eigenvectors, we were coming short. That is, you have an eigenvalue. That eigenvalue is a repeated root. You try to go ahead and find the eigenvector. There isn't any. Good news with the symmetric matrices is that that situation doesn't happen either. There's a full set of eigenvectors all the time. You can't have anybody missing in action. There wouldn't be situations where eigenvectors will just go disappearing on you. You have a full set of then all eigenvalues are real, there is a full set of eigenvectors. What do you mean full set of eigenvectors? Here is a 3 by 3 matrix. If I try to find its eigenvalues, well, there are going to be 3 eigenvalues. That never is violated. But if I'm dealing with a 3 by 3 matrix, it could be that it has 3 eigenvectors, it could be as 2 eigenvectors, it could be as just 1 eigenvector. From the start, all sorts of things are possible. With symmetric matrices, we have an additional advantage. From get-go, without going through the torture of finding them, we are going to know that it is going to have a full set of linearly independent eigenvectors. It's going to have 3. It's going to have a full set of eigenvectors. So if A is n by n, it's going to have n linearly independent eigenvectors. Okay. Good thing is that's not it. Good news keeps coming. What are the kind of vectors that you like most? What kind of vectors are the easiest to deal with? You start with your very first course in physics. What are the very first set of vectors you actually study there? What are these guys called? IJK. Those are the nicest set of vectors for you guys to work with. Here's another good news. What do you think it is? For symmetric matrices, your eigenvectors either from get-go are like these, or you can make them to be like these. Meaning what? Well, they are not going to line up exactly as IJK. That's going to be too much of a good thing. That's not going to happen. But in a majority of cases, the eigenvectors that you have are going to be IJK, like for 3 by 3, it's going to be IJK just rotated in space. It is pointing in some other direction, but essentially they are going to act like the IJK vectors that you had in physics. So the way we want to say it is that the eigenvectors are first of all perpendicular to each other. Except that we need a little bit of a fine print to make that to be true without being sued by anybody, and that's the following. The eigenvectors for, here is a fine print, for different eigenvalues are perpendicular. So if you know one eigenvalue is different from another eigenvalue, then the 2 eigenvectors that correspond to those 2 guys are perpendicular to each other. That's a very nice result. So if you know that your all values are all different, then you are going to have 3. So you're going to have 3 different eigenvectors, and from get-go they are going to be all perpendicular. So here is a fine print. They got to be different. What's important about that? Well, let's go back and take a look at the simplest matrix you can have. Simplest matrix you can have is just the identity. Is that right? Let's just keep it a small size. Here's the identity matrix. Who are the eigenvalues? What are the eigenvalues of this thing anyway? So it has to be immediate. And what does lambda turn out to be? Just 1 and 1. So eigenvalues turn out to be the same. Who are the eigenvectors? What matrices are there that if vectors are there that if I multiply with my matrix, it just gets multiplied by the eigenvalue. What did we say this one is? Just 1. So what are the vectors x such that if I multiply it by a, I get x? Any vector. Like life here is too good. You don't have to do anything. Any vector is an eigenvector. Any vector is an eigenvector. Obviously, they are not going to be perpendicular. Is that right? You say any vector is an eigenvector. Well, pick two vectors, pull them off the hat. They're not going to be perpendicular to each other. So that's the reason for this. But we are going to save ourselves. If any vector is an eigenvector, you can always find two eigenvectors that are perpendicular to each other. Is that right? So any vector is an eigenvector. If you pick two of these eigenvectors randomly, they are not going to be perpendicular to each other. But you always have the choice of picking two that are perpendicular to each other. So that is the next good news, that you can always arrange them, choose them skillfully and carefully so that they will be perpendicular to each other. So let me write that. Okay, even if the eigenvalues turn out to be the same, you can go inside of that particular subspace and pick your eigenvectors and push them open until they are perpendicular. Always the eigenvectors can be chosen to be perpendicular now, other than perpendicular, I, J, K have another property that makes them kind of extra nice. What is it? Well, yeah, basis. And what's their length? What? No, just to make things like a yardstick and have a unit length, it's nice to have, hammer them until they're all of the same size, as opposed to one sticking out 10 feet long and the other one just 2 inch long or something like that. So once you have your eigenvector, you can always cut it down to size, whatever size you want. So B okay, so you make them as much as possible to look like IJKs. First of all, they are perpendicular. Second, you cut them down to size so that they are all unit length. Such a collection of vectors which have these two properties are called orthonormal. Okay, ortho is like when you say orthogonal, something is perpendicular to another one. So that is the concept of perpendicularity. And normal is used in mathematics to indicate something is of unit size. So this one means 1, and this one means two things are perpendicular to each other. Okay? You didn't think you're going to get this much out of such a simple property, but the good news continues. There is one huge advantage coming up. Remember when we were doing the matrix factorization, what was our factorization formula? We had A times matrix of eigenvectors was equal to what? What did I have on the right hand side? V lambda, very good. And then if I want a matrix factorization formula into its eigenvectors, what did I have to do? V lambda, V inverse. And V inverse is another torture to get. In general, to get the inverse of a matrix, it's a huge effort. Here is our final good news. If you have already arranged your eigenvectors to be a collection of orthonormal set, this vector, this matrix V is made out of things that look like ijk's but rotated in space. That situation deserves such a importance, such a attention. They reserve a special letter to indicate that. They show that by Q. Q reserved for a matrix whose columns are just like ijk. They are of unit length and they are perpendicular to each other. Well, what is big deal about that? The big deal is finding V inverse is trivial. All that you need to do is to turn the matrix around. Just turn it around. Just flip it around to get its transpose. Isn't that a huge relief? You don't have to get the inverse of a matrix, which is a very expensive process. So good news number 5 is the following. Well, first let me just state in general maybe. If the columns of a matrix Q are orthonormal, then first of all that matrix has an inverse. Second, finding the inverse is trivial. Then Q inverse is same as Q transpose. You remember what the transpose is, right? You're flipping the matrix across its main diagonal. You just you identify the diagonal. Whoever is up here comes here, and whoever is down here goes up there. That's all. As simple as that. So, so let me separate good news number 6 as the following. If the eigenvectors of a real symmetric matrix are written as, now it's a peculiar terminology here, that matrix is referred to as orthogonal matrix, but let me not even write that down. If the eigenvectors of a real symmetric matrix are written as columns of then so the matrix factorization formula that we had before is gonna have Q lambda Q transpose as opposed to the V lambda V inverse that we had before. Instead of V we are writing Q. What happens is that V inverse just becomes Q transpose. So huge number of properties that come out of a very, very simple simple to verify assumption. Now to show all of these things takes quite a bit of time. What I'm going to do is to show you a simple case that let's just do one of these things at least. Perhaps one of the few proofs in this course that we are going to offer. that eigenvalues are real. We didn't do that many proofs in this course, just an introductory course. If you take an advanced course in linear algebra, everything we are saying is going to be established rigorously in that course, as opposed to being just stated or just verified. But let's see if we can do at least one. To do that, we need a little bit of a practice with complex numbers. Since I'm not going to assume that everybody is up to speed with respect to complex numbers, I'm going to give a brief review of complex numbers. So here's our aim. Our goal is the following. Show eigenvalues of a symmetric matrix are real. Notice that we are really making a grand statement, because there are so many such matrices out there, and we are saying all of them have such a property. Well, real means what? Real means as opposed to being a complex number. Who is a complex number? So complex numbers as opposed to being a complex number. So let's write down some complex numbers, like traditional notation for complex numbers like z and w and such, like x and y are typically reserved for the reals, and z's and such typically show up to indicate that something is complex. What is complex? Say 2 plus 3i. That's a shorthand for 2 plus 3 square root of minus 1. Using this notation of square root of minus 1 causes lots of kind of arithmetic mistakes down the road. In math, it's customary to abbreviate it as I. In electrical engineering, those of you who have taken courses there, instead of I, what do you use there? You use J for some reason. I don't know. Does anybody know what's the reason? They just want to look different from mathematicians, that's all. Anyway, so oh, I see. This conflicts with the caret symbol. Okay, good observation. Okay, let's take another one. Say 5 plus 7i. Just quickly go through this. What is z plus w? Well, before we go there to doing arithmetic, let's just do a little bit of terminology. This portion that doesn't have any I next to it is referred to as the real part. The portion that is right next to I is called the imaginary part. Notice we don't say imaginary part is 3i, we say imaginary part is 3. It is assumed that, well, later on you're going to multiply it with I. Okay, so that's a real and imaginary. Well, real and imaginary, like oil and water, don't get mixed. We are just writing them next to each other. If I want to add two complex numbers, what do you think I'm going to get? 7 plus 10i. So this is no surprise. If you want to subtract them, minus 3, minus 4i, and so on. What you have to be careful about is multiplication and division and powers, things like that. We just have need for multiplication, so let me just do that one. You do the other one, maybe reviewing some books. Suppose we want to multiply z plus w. So long as you remember that I, when it is multiplied by itself, or I squared, what is that? Again. So long as you're careful about that, everything just flows according to whatever you did in plain old algebra. So there isn't much of a surprise. You say 2 times 5, 2 times 7i, 3i times 5, plus 3i times 7i. Well, no surprise here. That's 10. What do you think is 2 times 7i? 14i. In this one, 15i. In this one, negative 21. That's the only place you are being careful about. So negative 21. So 10 minus 21, that mixes to minus 11, and these two mix up to 29i. So it's a multiplication, but the product of the two imaginary parts create a negative real which mixes with the product of the two reals, and that is where interesting things and complications start to show up. Now, there is a very important situations where the product of two complex numbers turns out to be a real number. To introduce that, we talk about conjugate. If I have a complex number and I conjugate it, it's called complex conjugate. Okay, what's the complex conjugate of 2 plus 3i? 2 minus 3i. Or let's do the following. Suppose, as another practice, suppose I have 5 minus 11i. I want to conjugate this whole thing. What am I going to get? 5 plus 11i. So conjugating, if this was negative, becomes positive. If it was positive, so let me write that one also. 2 plus 3i. If I conjugate it, I get 2 minus 3i. What is deal about this one? So let's take a matrix. Let's take a complex number 2 plus 3i. This is your z. Let's multiply it by its conjugate, 2 minus 3i. This is z bar. Okay? Let's do it again. 2 times 2. 2 times minus 3i. 3i times 2. Then 3i times minus 3i. Well, what are the interesting things that are going to happen? This is 4. These two, you say what? They cancel out. Whatever it is, one has the opposite sign of the other one, so the net is 0 here. And another interesting thing happens here. 3i times minus 3i. Yeah, you have 3 times minus 3. But then you have I times minus I. I times I is I squared. Is that right? 3 times minus 3 and I squared. What was I squared? Negative 1. So this negative cancels the other negative. You get positive. So you get 4 plus 9. So how can we make a shortcut? Suppose I have I A plus BI. Some general complex number, a and b, both of them real numbers. I multiply with its conjugate. What am I going to get? So suppose a and b real. So what happens? A times a, I will have a squared. Bi times minus bi, I have plus b squared. And the other two terms vanish. Well, what does this remind you of? A squared plus b squared. Going back to elementary geometry, so that's one of the motivations and can be built into a whole theorem that really when you're talking about complex numbers, you're talking about a complex plane. In that plane, you have stepped to the right by A, you have stepped up by B. This thing that you are getting here, this point that previously was shown by as a vector AB, you can think about it as A plus BI. And that A squared plus B squared is really your this is square root of A squared plus B squared is the size of that vector. So for that reason they refer to it as the magnitude of Z. So they think about this thing. This vector can be also shown by this complex quantity z, and this is thought about as z squared. So magnitude of z squared, or absolute value of z squared, is sum of square of the real and imaginary component of it. It's just repeating the Pythagorean theorem. So let's paraphrase. Z times z bar is equal to magnitude of z squared. An important thing about this whole thing is that what comes out of here is just a real number. Biggest thing that we need out of this whole discussion If you take a complex number, multiply by its conjugate, out comes a just pure, real, positive number. Okay, that is enough of introduction for complex, I suppose. Now, what we want to do is to have, for a grand finale of the course, is to show this as at least having one thing that we have proven in this whole semester. Just have that one. So now the idea is true for any size matrix. I'm going to limit myself to 2 by 2 so that we don't get drowned under a lot of algebra. So we are going to show real symmetric 2 by 2 matrix has real eigenvalues. So let's say A is symmetric. So on the diagonal I can have anything I want. Off diagonal we insist that they gotta be the same. So since you said it is symmetric, that means these guys better be same. On the diagonal we don't have any restriction. We also say it is real, means all of these things to begin with we are just dealing with real quantities. So suppose its eigenvector is xy and eigenvalue lambda. We show lambda is real. How do we show that? First, if this is the eigenvector and that's eigenvalue, then if I have AB, BD times X, Y, what am I supposed to get? Lambda times XY, is that right? If you are selling this to me as an eigenvector and that as an eigenvalue, then that means that you are telling me this is true. Next, well, what is this thing anyway? Let's just multiply it out. So AX plus BY, I multiply that row with this column, and BD is that right? Now here comes wrap it out of the head. I take this thing and multiply with the conjugate of this vector, that is. For reason that we are going to see shortly, I take x, y, bar. So I'm taking conjugates of these things, but there could be complex numbers. I'm taking their conjugate. I multiply it with okay, help me out in this multiplication. So the first item multiplies the first item, second item multiplies the second item. Let me write it out. X bar times AX plus BY and Y bar times BX plus DY. Help me to multiply it through. What do I get? X bar times AX. What can I write that as? Well, let's write it all out first and then you think about it. B what did we say about multiplying a complex number with its conjugate? What happened? Yeah. That was that hypotenuse squared, which is what? The important thing we said about that is that it is a real number. How about this guy? That is also a real number. Y times y bar is just some complex number squared. What is left is the stuff in between. B times x bar y plus y bar x. What do you think going on with that one? This is really the conjugate of that one. If you take the conjugate of x bar y, you get y bar x. And when you add them, what are you going to get? Yeah. Let's just, we can prove it, but let's just to open up the discussion. Let's take an example. The proof is just as straightforward as example. So suppose your x was 2 plus 3i and your y was 5 plus 7i. First of all, what is your x bar? 2 minus 3i. What is your y bar? Now, you are talking about x bar times y. Help me out with x bar times y. 2 minus 3i times 5 plus 7i. And later on, we are going to do the other way around. X, y bar, that is 2 plus 3i. This is your x. This is y bar. We are planning to multiply these guys out and then adding them up all later. Anybody cares to guess what's going to happen, what kind of simplification is going to happen in that whole process, Before drowning all the little arithmetic, anybody can see a few moves into this chess game. It becomes what? Well, let's go ahead and multiply it. So 2 times 5 is 10. Minus 3i times plus 7i, what is that? Plus 21. Now, how about the other one? 2 times 7i, let me write it out, 14i, minus 3i times 5. Now, let's do this one. How about the real portions? 2 times 5 plus 3i minus 7i. Who's that? Plus 21 again. What happened? Both of these i's got flipped. So you have an extra minus times minus. But that's not going to make a dent in the final product. But how about the I portion? What did I do here? Okay, 2 times minus 7i, what do I have? Minus 14i. And 3i times 5. Oh, I made a mistake here, is that right? Everybody got confused. Okay, 3i times 5, what do I have? Now, if I were to add these two guys, what do I get? Well, let's simplify. This is 21 minus I, or 31 minus I, and this one is 31 plus I. They are complex conjugate of each other. In fact, you can show that if you take x, y, conjugate the whole thing again, the bar flips on top of the other one. Well, so what? The so what of it is that if you add them, what happens? It's going to be 2 times the real part, which the important thing is that it's going to be a real number. Why a real number in general? Because one of them is the conjugate of the other one. If you add two numbers that are conjugates of each other, means one of them has a plus I, another one has a negative I, they just cancel each other out. So again, what is it that we got out of all of this? We got out of this that this thing is real. X bar y plus y bar x, all the i's cancel out. and what you get is real. So what I have is that if I take the conjugate of my eigenvector or multiply with the result of this multiplication, all I get is something real. Now let's go back here. So let's do it also to this one. I took x bar, y bar and multiplied by that, but that is supposed to be same as this. So I take x bar, y bar, multiplied by so what is this thing? This is x bar, y bar, and that is lambda x, lambda y. Help me out with this multiplication. X bar times lambda x, what is that? Lambda x bar times x, what is x bar times x? And y bar times lambda y, what is that one? Lambda times y squared. So we have the following. This product that we carried out, this was one answer, this was the other answer. They got to be same. So what can I get out of that fact that these are same things? So let's write out, let me erase some and make some room for what we are making. So what we are saying is that over there I have lambda, let me factor my lambda. Lambda times x squared plus y squared is equal to a times x squared plus b times x bar y plus y bar x plus d times y squared. Now somebody tell me the punchline. Okay, you got this thing. What is it good for? What was our aim? What were we trying to establish? What were we trying to establish? Who is supposed to be here? We want to show that lambda is real. How does this show that lambda is real? Let me help you out. Who is lambda? Lambda is equal to, here on the right hand side, why does this show that lambda is real? Yeah, everything on the right hand side is real number. We went through that exercise to say this is real. From beginning we insisted A, B, D are real. These are magnitudes. They are all real. This is real. This is lambda is equal to this. Lambda gotta be real. Okay, so if you are interested in following math, this is the kind of thing you should get yourself ready to digest and swallow and show interest in and pursue and stuff like that. We avoided most of these things, but that's where much of mathematics lies. Okay, so we showed that the eigenvalues of a 2 by 2 symmetric matrix are real. Same thing applies to any size matrix. The proof is exactly the same, but